In this lecture, I'm going to tell you about the RSK correspondence. The first and main ingredient in the RSK correspondence is Schensted's insertion algorithm. What this does is it takes a standard, semi-standard Young tableau P and inserts a number A into it. So for example, we could have the tableau 1 3 3 5 8 2 4 6 6 3 5 8 4, and let's say we want to insert 3 into this tableau. So this is a semi-standard Young tableau here, in the sense that every row is weakly increasing and every column is strictly increasing. And we're going to insert this 3. It's going to find its place somewhere up inside this tableau, and maybe some of the other letters in this tableau as well are going to get moved around a bit. So let me just make a copy of this and we'll do the insertion. So the first step is to insert 3 into the first row of the tableau that we have here. So what that means is that you look for the first entry in the first row that is strictly greater than 3. So here this 5 is strictly greater than 3, and so what I'm going to do is I'm going to put the 3 in the place of the 5. So let me just write this down: to insert A into the row A1, A2, AN, find the least I such that AI is greater than A. Put A in place of AI and we will bump out AI from the first row. So what we are going to do is we are going to take this 3 and we are going to put it in here. I'll just show it in a different color, and we are going to bump out what was there in the earlier place, which was the 5. And now what we do is we recursively apply this algorithm. 5 is inserted into the second row. Now again we follow the same algorithm. We look for the first number in the second row that is strictly greater than 5. Let me just copy this again and we'll do it again in the next step. So what's the first letter in this row that's greater than 5? Well, it's 6. So the 6 gets bumped out and 5 comes to rest in its place. So we have this 5 here, and now this 6 gets bumped out, and so it has to be inserted into the third row. And by now you're probably quite familiar with what's going to happen next. We are going to try to insert this 6 into the next row, and so what happens is that 8 is the first letter here that is greater than 6, and so we are going to put the 6 in its place, and we are going to try to insert 8 into the next row. But this 8 is greater than or equal to all the entries in this row, and so then we have a different rule for that. So let me add that rule here. In case A is greater than or equal to AN, then A comes to rest at the end of A1 up to AN, and nothing is bumped out. So So this 8 comes to rest here, and nothing is bumped out. If something were bumped out of here, then it would come to rest in the next row, which would be a new row that would be started. But here there's nothing, and so the 8 just comes to rest at the end of the 4th row. So now we need, I want to convince you that this process is actually reversible. Well, let's just stare at this tableau we have here. And when I say it's reversible, I mean it's reversible provided you know what was the last thing that was inserted. So provided we know that this 8, so whenever you do an insertion, a new box is going to be created in the tableau. In this case, the box is here in the 4th row and 2nd column. So we know that this 8 was inserted here, and so we know that 8 was bumped out of the previous row. Suppose we didn't know that these were the numbers that were bumped out. We just had let's just put them in blue, so you can no longer tell who was bumped out, who bumped out the 8. So the question now is the murder mystery: who bumped out the 8? And the answer to that is that it is the last. So if AI was bumped out by A, then firstly we know that A has to be less than AI. And we also know that everything to the left of A has to be less than AI. So what we know is that A is the last entry in the row that is less than AI. So in this row, the last entry that's less than 8 is 6. So this 8 must have been bumped out by the 6. So what we'll do is we'll put this 8 in the place of 6. Let me just copy this. So what we know is that this 8 was here, and that it was bumped out by a 6. So we know that it was bumped out by a 6. Now where did the 6 come from? And to find that out, you must look for the last entry in this row that is strictly less than 6. Well, the last entry in the second row that is strictly less than 6 is this entry 5. And so the 6 was bumped out by 5. And so we must have had a 6 here. And it must have been bumped out by a 5. And so again, repeating this process, we ask, where did this 5 come from? Well, look for the last entry in the first row that is strictly less than 5. Well, it is this entry 3. So this 5, in fact, was bumped out by 3, and it used to be here. So we have that originally we had 5, and we must have inserted 3 in the first place to get this process rolling. So let's just go back and check if this is what initially indeed happened. And we see, yes, it was indeed a 3 that we inserted into this tableau with first row 1, 3, 3, 5, 8. And we have recovered the letter which was inserted just from the information of what was the new box that was added into the tableau. So what we've seen of Schensted's insertion is that given a semi-standard Young tableau and a letter or a number, we can insert that number into the tableau and we will have created a new box. After completing the whole process, we would have created a new box. And if we know what that new box is, we can reverse the process and recover the number that had been inserted and the original tableau. However, we still need to check that this new tableau that we create is in fact a semi-standard Young tableau. So this is the final tableau that we got in the insertion process, and you can see that it actually has weakly increasing rows and strictly increasing columns. This will always happen. Why? So here's the notation that I'll be using. I'll use P1 is equal to PA to denote that P1 is obtained by inserting A into P. Okay, so now the claim is that P1 is also a semi-standard Young tableau. So suppose we had the row A1, A2, AI, AN, and we were inserting A into it. And suppose the next row of the tableau has a letter, let's say B1, B2, and here we have BI. And suppose this AI, this is the least I such that AI is greater than A. So what will happen is that this A will come here. We have AI is greater than A. This A will come to rest here. And now, since the original tableau was semi-standard, we know that BI is greater than AI. So when we insert AI here, then what will happen is that this BI is already greater than AI. So either AI will replace or should we say bump out BI or something to the left of BI. And that means that what we get in the entry below A will be strictly greater than A. And therefore, the new tableau will still have strictly increasing columns. Now, before we proceed further, let's just summarize what we have done so far. So we have a function insertion P comma A goes to P insert A. And let's say if we know P insert A and the cell the new cell in P insert A, we can recover both P and A from the semi-standard Young tableau P insert A. One small lemma which will be important later on is that if A is less than or equal to B, P is a semi-standard Young tableau, P1 is P insert A, P2 is P1 insert B, and the new cell of P1 lies in row I and column J, and the new cell of P2, the cell which was not in P1, lies in row I prime and column J prime. Then we can conclude that J prime is strictly greater than J and I prime is less than or equal to I. So for example, in this insertion process that we did here, I is 4 and J is 2. That's the new cell that was created. So now what we are saying is that if we were to insert one by one two numbers, one that is the first number and then a number that's not less than that, then the new cell that will be created will somehow have this relationship that the second new cell that is created will lie in a row equal to or above the first new cell, but strictly to the right. And to prove this, let's just suppose that the first row of A is A1, A2, AN. Of P is A1, A2, AN. Now let's look at a few different cases. Case 1, suppose AN is less than or equal to A, and we know that of course A is less than or equal to B. Then P prime has first row A1, AN, AB by the second rule that we have for insertion. If A is greater than or equal to all the entries, then A comes to rest at the end of A1, A2, AN. So then both A and B come to rest at the end of the first row, and so they lie in the same row, and B comes to rest strictly to the right of A. So this case is okay. Case 2, let's suppose that A is less than AN, but AN is still less than or equal to B. In this case, B still comes to rest at the very end of the first row, but when AN is inserted, a new cell is created in one of the rows below the first row. And so again, it's clear that J prime will be strictly greater than J, and I prime will be less than or equal to I. In fact, in this case, I prime will be strictly less than I. And finally, case 3 is when both A and B are less than AN. In this case, A bumps out AI and B bumps out BI, then AI has to be less than or equal to BI. And so now what will happen is that first AI and then BI will get inserted into the second row of P. And using induction, we can conclude induction on the number of rows of P. We can conclude that J prime is greater than J and I prime is less than or equal to I. We're now ready to describe the RSK correspondence itself. So I'll use the term integer matrix to denote a matrix, to mean a matrix with non-negative integer entries. Okay, not just any integers. You are not allowed negative integers, only non-negative integers. So for example, here is integer matrix. This is a rectangular matrix with 6 rows and 7 columns. The first step in the RSK correspondence is to recode an integer matrix in terms of what is known as a bivector. What you do is you read the matrix along the rows from left to right. So first you read the first row from left to right. Every time you come to an entry of the matrix, you note down its row number, and a non-zero entry of the matrix, you note down its row number and column number, and you note it down with multiplicity equal to that entry. So here we have an entry which is non-zero. It's in the first row and third column. So I will note down 1, 3 with multiplicity 1. Now let's go on to the second row. Here's an entry. It's 2, 1, 2, 3, 4, 5, 6. 2, 6 with multiplicity 2. So I write 2, 6 down 2 times. Then I have 3, 1, 3, 2, 3, 3, 3, 4, 3, 6. That's from the third row. In the fourth row we have 4, 3 and 4, 5. In the fifth row we have 5, 1 2 times because of this 2 over here, and then we have 5, 2 and 5, 4. In the last row we only have 6, 7. So we have taken this matrix and coded it in terms of the bivector. You can recover the matrix from the bivector. Well, you just start with the 0 matrix, and then every time you see I, j in your bivector, you add 1 to the ijth entry of your matrix. There's some ambiguity here in the sense that if I were to add zeros to the right or to the bottom, 0 columns to the right of the matrix or 0 rows to the bottom of the matrix, then this bivector would not change. Another interesting feature of this bivector is that the first row is weakly increasing because we were reading the matrix along rows. But in this first, if you look at the sections of the bivector where the first row is constant, then the second row is weakly increasing in each such segment. So this bivector is a sequence of the form I1 J1, I2 J2, and so on, where I1 is less than or equal to I2, less than or equal to I3, and so on. And if Ik is equal to Ik plus 1, then Jk is less than or equal to Jk plus 1. Okay. So now what we'll do is we will construct 2 semi-standard young tableaux starting with this bivector. I don't need these subdivisions here. We'll just look at. Okay, so this I'll just do this in a table. So we are going to have 2 tableaux, P, which is called the insertion tableau, and Q, which is called the recording tableau. We start with both these tableaux empty. And now what we do is we will insert the entries of the second row of this bivector into P, and we will record where the new cell was created in the tableau Q. And what we will do is we'll actually record, if we are inserting the J, we are going to record the position with an I. So let me show you how this is done. So to start with, we just have the empty tableau, and we have to insert 3 into this. Now that means that there's nothing in this tableau. The first row has nothing in it. The 3 just comes to rest at the end of the first row. So this is step 0 if you wish. In step 1, we have the P tableau is 3, and we record that the new cell was created in the first row and first column we insert this, we record it by putting this 1 over here. Okay, this will become clearer as I go along. Now the second step, so we are done with this here. Now the second step, we must insert 6 into this. So we get 3, 6, and now let me just make this a little tighter so that I'll be able to finish it all in a reasonable amount of space. So yeah. So we have 3, 6, and what has happened is that this 6 has come to rest in the first row, second column. So what I'm going to do is I'm going to put this 2 over here in the new cell that has been created. Now let's look at what happens next. We have another 6, so let's insert that, and so we get 3, 6, 6. A new cell has been created in the first row, third column, so this 2 goes in there. And now I must insert the 1. Now something interesting happens. When I insert the 1, it bumps the 3 into the second row. And a new cell has been created in the second row and first column. And so this 3 over here goes into that place. So I'm putting the I coordinate into the Q tableau and recording the new place that was created. At the fifth step, I will be inserting this 2. And so I'll get 1, 2, 6, 3, 6. And so now I have 1, 2, 2, 3. And the new cell that was created is the second row and second column. It's a 3. And now I put the next 3 into this. Sorry, this here was a 2. Now I'm putting the 3. And I get 1, 2, 3, 3, 6, 6, and this is 1, 2, 2, 3, 3, and this 3 also came with the 3, so I get a 3 here. I can continue in this manner. Continuing in this manner, we are finally able to compute the insertion tableau P and the recording tableau Q associated to the original integer matrix that we had started with. Now we've already seen that P is going to be a semi-standard Young tableau, namely with weakly increasing rows and strictly increasing columns, and using the properties of the two-line array that I had talked about earlier, you can also show that Q will be a semi-standard Young tableau. Now, how many times does the integer I appear in P, and how many times does the integer I appear in Q? So you note that the number of times an integer, well, j occurs in P is the number of times it occurs in the second row of this two-line array, which is just the sum of the jth column of this integer matrix. For example, the let's say the sixth column of this matrix, well, 1, 2, 3, 4, 5, 6. Yeah, the sixth column of this matrix has a sum 3, and the number of times you see 6 in the second row of the matrix is also 3. 1, 2, and 3. There are 3 6s, and so there'll be 3 times that we're inserting 6, and indeed you see that there are 3 6s in the P tableau. So the number of times j occurs in P is equal to the sum of the jth column of A. And the number of times I occurs in Q is similarly the sum of the ith row of A. Now let us try to see why this correspondence is reversible. Suppose we were to just start with the end result of this process, namely the tableau P and Q. So So we have P and Q, and can we say where these P and Q came from? So we know that we were inserting elements in increasing order of the I coordinate, and so we know that this 6 must have been the last thing to be recorded. And so how could this 6 have been recorded? Well, the 7 must have been inserted. So we know that at the very last stage we had 1 1 1 2 4 2 3 3 5 3 4 6 6 6, and here we had 1 2 2 3 3 3 3 3 4 4 4 4 5 and 5, and here we were inserting a 7, so that means the j, the last j in our 2-line array must have been 7, and the last I in our 2-line array must have been 6. Okay, so this is what the situation was just before the 15th step. Indeed, you can see we had inserted a 7 and we had recorded a 6. And the last entry in our 2-line array was 6, 7. Now, what happened in the 14th step? So we have here, we know the largest number in this recording tableau is 5, but there are 2 of them. So the question is, which of these 5s appeared last? We've already shown in this lemma, and that was in fact the purpose of the lemma, that if you insert A and B where A is less than or equal to B, then the new box created by B lies strictly to the right of the new box created by A. And so we must look for the rightmost box containing a 5, and that would be the box that was added last. So what we know is, let me just copy this. What we know is that this 5 was the box added last, and so that means that this 6 here was bumped out from the previous row. And what could have bumped out the 6? Well, we already know that the Schensted insertion process is reversible. This 6 must have been bumped out by the last element in the previous row, that is less than 6. And so this 6 must have been bumped out by the 5 here. And so there must have been a 6 here, and we must have inserted a 5 into this row. And who bumped out this 5? Well, it must have been this 4. So what we know is that before this 6 7, our 2-line array had a 5 and a 4. And you can just continue in this manner and reverse the entire process and recover from the tableau P and Q this 2-line array, from which in turn you can recover the original integer matrix. So what we have is the following theorem. Let the RSK correspondence gives rise to a bijection from the set of integer matrices onto the set of pairs of semi-standard Young tableaux of the same shape so we'll call this correspondence A goes to RSK. Moreover, the number of times that I occurs, let's say J occurs, so let's say this is P comma Q, the number of times that J occurs in the insertion tableau P is equal to the sum of the jth column of A and the number of times that I occurs in Q is equal to sum of the ith row of A. For example, if we were to restrict the RSK correspondence to n by n permutation matrices, then those would be matrices whose row sums and column sums are all equal to 1. And therefore, both P and Q would be tableaux where each integer from 1 to n occurs exactly once. And these are called standard Young tableaux. So in particular, the RSK gives rise to a bijection from Sn to sum over all lambda, tab lambda squared, where tab lambda denotes the set of all standard tableaux of shape lambda, where lambda runs over all partitions of n. In this lecture, I have sketched somewhat cursorily the Robinson-Schensted-Knuth correspondence. I would urge you all to take a look at Donald Knuth's original paper on the topic. It's called Permutations, Matrices, and Generalized Young Tableau. It appeared in the Pacific Journal of Mathematics in 1970. So here he introduces the RSK correspondence and proves some fundamental properties of it in great detail.